In this video, let's talk about the application of exponential. So here are the formulas you need and some examples. In these first two examples, it's talking about growth and decay, which we have already had a whole extra lesson on. And so I've already set these up so you can just see some more good examples. The annual rate of increase for the U.S. population in 2000 was 1.24%. The U.S. population in the year 2000 was 281 million. So notice I have put the initial amount of 281 out front. It's increasing, so I put 1 plus the rate. Notice we write the rate as a decimal, so I put 0.0124 to represent 1.24%. And then whenever we write out a model to predict something, we have to always have a place for our input and our output. So in this case, I just left those as A, which would be our final amount, our output, and time, T, which is our input. You leave those in there to represent the model that you're predicting with. Then in the next question, it says use this model, which we wrote down, to predict the population in 2018. The only thing I needed to do was put in time was 18 because it went from the year 2000 and now they're asking about 2018. So you just plug that in, type everything in your calculator, and then you should get 350.8 million people. And like I say, that was just another good example of growth, which you've already seen in another lesson. In the second example, it said, suppose you want to buy a used car that cost $11,800. So that was our initial amount, P. The expected depreciation of the car is 20% per year. So I wrote that as 1 minus, since it's depreciating, it's going down in value. And then 20% is where I got my 0.2. We always write it as a decimal. Then you're writing a model. So always leave room for your input, which is time, and your output, which would have been the final amount the car would be worth. And then it said, estimate the depreciated value of the car after 6 years. So I just plugged in time was 6. And I got $3,093.30. Okay, so now let's look at some other formulas we're going to see from time to time. There's one that we call the PERT formula, and it's when it's saying continuously compounded interest is the type of interest that you're dealing with. And you set up A is still your final amount, P is still the initial amount, E we're going to type in the calculator just like it looks, a lowercase e, and then we have R is the rate and T is time. So it's pretty straightforward for most of these. We say, let's see, you invest $1,300 at an annual interest rate of 4.3% compounded continuously. Let's highlight that because when you see that phrase, and they could also switch the words up on you and say continuously compounded, and that means the same thing. It says, how much will you have in the account after 5 years? So let's set it up. If we want to know how much we will have, that's our final amount that we're going to figure out. So put A, that's what we're going to figure out. $1,300 was the initial investment. We're going to put in the E. Rate, we still need to put as a decimal. So 4.3%. If you move the decimal over 2 places to the left, you get 0.043. And then time was 5 years. All that is in the exponent. Now let's type that in and see what we get. So you just type in 1,300. Don't put in A equals. You need the lowercase e. You can either type it here in the Desmos keyboard or on your laptop keyboard. And then hit that little A exponent B button. And then put 0.043 times. Oh, see how that drops down? You want to keep it all together. So go back to your exponent and make sure it's in parentheses. So you can put it all together up there and put 0.043 times the time, which was 5 years. And then that would be the right amount. So we would have $1,611.82 in the account after 5 years. All right, let's look at another example of that. So Susie invests $2,100 at an annual interest rate of 3.75%. compounded continuously. So you only use this formula when they use those words. If they don't use those words, then it might just be a growth or decay problem, and you don't need this formula for those. And it says, how much will she have in the account after 10 years? So will she have, that's still the final amount we're looking for. So put A equals, she invested $2,100, so that's our initial amount. And it's always got that little lowercase e. Our rate was 3.75, so move your decimal 2 places to the left and make it 0.0375 times time, which is 10 years. So once you get everything set up, you can just type that into Desmos. And we're really just using Desmos as a calculator for these. So 2100, no comma, put a lowercase e, use the exponent, the little AB exponent key, and put 0.0375 times 10 all together in the exponent. So make sure you get the right amount. And then we get $3,055.48. Again, the PERT formula, that formula is only used when you're given continually compounded interest. So let's look at the next type of problem you might see. It says compounded interest, and N is how many times a year the interest compounds. And then there's different values for N. So for instance, if they say that it compounds biannually or semi-annually, that means twice a year. So we would say N equals 2. We'd say N equals 4 if it's quarterly, for example. That's a popular one they like to say. N equals 12 if it's monthly. So those are some of the most popular ones. If they say 3 times a year, N would equal 3. So it's whatever they tell you is happening. So this one says, and we use this formula. So let's look at the formula again. A is still our final amount. P is still your initial amount. R is still the rate. T is still time. And then you have this extra variable N because it means it's how many times a year that the interest compounds, like it says right there in that box. So we've already typed that in. But that's what we're looking at that's different for these problems. So whenever they mention a amount of time a year your interest compounds, it's not continuously and it's not just growth or decay. You've got to use this formula. Okay, so let's get started. If you have a bank account whose principal equals 1,000 and your bank compounds the interest twice a year, so that means N would equal 2. The 1,000 is the principal. That's why we call that P. It's like your initial amount. You have an interest rate of 5%, so R would be 0.05. And it says, how much money do you have in your account at the end of the year? So I'm going to scoot it over so you can see that formula again, nice and clear. At the end of the year, so that's our final amount we're looking for, so put A equals. We have the initial amount, which was 1,000. It's always 1 plus. Then the rate was 0.05. Divide that by N, which was twice a year, so you put 2 there. And notice N is in 2 places. You do put that number in both places when you're filling this in. And then they said the time, let's say they said end of the year, we had the rate twice a year. So if it's just 1 year, it sounds like, then that would just be 1. And let's type everything in. So we have 1,000, and then in parentheses, put it like it looks. 1 plus 0.05 divided by 2. Notice it shows up fine when you type it just like that. And then to your exponent, and we would put in 2 times, and in this case it's just a 1, but a lot of times that would be some other number. And so we end up with an amount of $1,050.63. And let's look at another example of this one. If you deposit $6,500 into an account paying 8% annual interest compounded monthly, how much money will be in the account after 7 years? So time would be 7. Our rate would be 0.08. 6,500 is our initial amount, so that's going to be our P. And monthly means that in number of times a year is 12, because there's 12 months in a year. And then we're still looking for the final amount. So let's put A equals 6,500 for the initial amount. 1 plus the rate, which is 0.08, over N. Remember what our formula looks like. We got to divide the rate by the number of times a year that it compounds, which was monthly. So let's put 12. Then also put 12 in the exponent on the outside of the parentheses, times 7 for our time. And then we just need to carefully type all of that into Desmos this time. So 6,500, 1 plus 0.08 divided by 12, and then put your exponent and group those together. So 12 times 7 all together in the exponent. And so in this case, oh, I have the wrong sign right there. I was wondering. I need a plus sign right there. That looks better. So 6,500, 1 plus 0.08 divided by 12, and then 12 times 7 is my exponent. So we would have a total of $11,358.24. Okay, there's one more formula we need to look at to wrap up these notes. It's called half-life. So if you've been in science class and you've been talking with your science teacher about like when something is decaying on like a petri dish, and you start out with like a whole bunch of bacteria or organisms on a petri dish, and then after a certain period of time, we call it a half-life when only like half of them are left on this petri dish. That's considered a half-life, how long it takes for something to decrease by half. And so the formula goes, A is still your final amount, P is still your initial amount. I'm gonna grab a new color. So A is final, P is initial. Notice T is still time, but H is now the time it takes for that half-life to occur, and that has to be given in the problem because otherwise they would not expect you to know about that. So the half-life of plutonium-239. Notice plutonium-239 is the name of an element. The 239 is not something we need to fill in for our formula. But the half-life of that element is 24,300 years. If a nuclear bomb released 8 kilograms of this isotope, how many years would pass before the amount is reduced to 1 kilogram? So they gave us a final amount this time. 1 kilogram would be the final amount. 8 kilograms was the initial amount. And they gave us the half-life, so that's our H. And then they're looking for how many years. So how many years is time? So let's fill everything in that we know. The final amount is 1. The initial amount was 8. And we need to put in 1/2 for the base. And then I need to scoot that down where I have a little more room to write. And so in the exponent, I've got to put time, which is what I'm looking for, divided by the time it takes for that half-life to occur, which is 24,300. And so what we can do to figure this out is we can actually set up a system of equations into Desmos because we want to figure out a variable that's in the exponent. And so let me grab another color. We're going to write down what we're going to type in. So let's put y equals what is on the left, which is just 1. And we're going to put y equals what is on the right of the equal sign. We're creating a system of equations so we can find what value of t would make those two things equal to each other. And systems of equations help us figure that out very nicely and easily in a calculator. So if we put in y equals 1 for one equation and then drop down to the second row in Desmos and type in the other side. So we have 8, we have a base of 1/2, not 12, we need 1/2. Let me get that straightened out. Okay, then we need an exponent. Now we know that Desmos does not like letters like T, so we're just gonna make that an X when we type this in. So it'll understand that that's our variable. So X divided by 24,300. Don't put any commas. Desmos doesn't like those either. And then we need to find where these touch. So I'm gonna hit the home button and I'm looking for where these are going to touch. So it's looking like, let's see. And if you click around up there, let's see. Let's go back to home. Let me use my wrench. So if you use this little wrench, you can actually make your x-axis get bigger quicker. So I'm gonna put like 5,000. And I can tell that they're getting closer now. So let's type that little wrench and then go to your y maximum value and make it bigger. Like let's say 10,000. See, they're getting closer together now. Let's do that one more time. Let's say that that would be 15,000. See if that helps. Getting closer. So then, there it is. Desmos will eventually give you the value where those are equal. So 72,900. It took us a little bit to figure out that X would be that long of a period of time. So that's how many years it would take for 8 kilograms of this isotope to reduce to 1 kilogram. So let's look at the last example. It says the half-life of cobalt-60, notice that's the name of the compound. The 60 is nothing we need to plug in. Is 5.26 years. So that's our H. So H equals 5.26. If 50 grams are left, so that's your final amount. After 15.78 years, so that'll be our time, how many grams were in the original sample? So we're looking for the initial amount. All right, so let's plug in. The final amount was 50. Initial amount is what we're looking for. We have a base of 1/2, and then we need to put time, which is 15.78 over the half-life, which is 5.26. Just like our formula said over here. So time over half-life is our exponent. Now in this case, we do not have to make this into a system of equations because we have numbers except for that p. So we can work with them, like our variable's not in the exponent, in other words. So what I'm gonna do is reduce this down to something that looks a lot nicer. So let's type in 1/2. In the exponent, type in what you see, which is 15.78 over 5.26. So you can basically take this whole part of this equation and get a number for it. You can evaluate it, in other words, and get a number for that. So 50 equals P times, now we have a value of 0.125, and that's much easier to solve than the last one was. So we just need to divide by that number and we get our initial amount. So 50 divided by 0.125 will just be 400. So 400, and I think they said grams. Yep, 400 grams was our initial amount. Okay, so that is it for a few more formulas that we need to work with application of exponential.